Okay guys, so we were talking about properties of addition of complex numbers. Let's continue with the same. Till now we have witnessed that two properties which are valid in reals are also carried forward as in a valid format in complex numbers. Addition in real numbers is commutative. Okay, addition in complex numbers is also commutative. Addition in real numbers is associative. Yes, addition in complex numbers is equally associative. Now there is one more property which is something that we are going to compare it in the case of reals as well and then conclude in complex. So regarding properties of addition of complex numbers, regarding properties of addition of complex numbers, third property says what? It says that there exists a complex number known as 0 plus 0 iota. Now 0 plus 0 iota is a complex number. It has real part and imaginary part as the real number 0. There exists a complex number 0 plus 0 iota which is the identity element in addition of complex numbers. Is it clear? There exists a complex number 0 plus 0 iota which is the identity element in addition of complex numbers. That means addition of complex numbers, with respect to addition of complex numbers there definitely exists an identity element. Now if I compare this property in the case of reals, what is that element in reals which is called the identity element in reals with respect to addition in reals? What is the identity element which does not change? If I am saying identity element with respect to addition, that means identity element is that element, that number which does not change the identity of the number to which it is added. If I am saying say x is, so this is some fixed number, x is the identity element in the collection of all reals with respect to addition operation. That means you give me any number, suppose 2. When x is added with 2, it does not change the identity of 2. You give me any number. When x is added to 3, it does not change the identity of 3. When x is added to minus 4, it does not change the identity of minus 4. When x is added to 7 by 99, it does not change the identity of 7 by 99. And likewise, if x is added with any real number, then it does not change the identity of that real number, and that particular x is 0. It is the number 0 which is such a real number that when it is added with any real number, it does not change the identity of that real number. This is called the identity element of the set of all real numbers with respect to addition operation. Exactly in a similar fashion, I am saying in the set of complex numbers, the complex number which stands as the identity element of the set of complex numbers with respect to the addition operation is 0 plus 0 iota complex number, right? When you add any complex number with 0 plus 0 iota, you get that complex number itself is the claim of this property. So let's prove the claim and establish this result as a valid one. Now, if I want to show that 0 plus 0 iota is the identity element in the set of complex numbers with respect to addition, that means I have to show that when 0 plus 0 iota is added with any complex number, it does not change the identity of that complex number. So I am saying let z be equal to a plus iota b, this be any complex number. Let this be any complex number. Let this be any complex number. I have to show that when I add z with 0 plus 0 iota, this complex number, then I get back Z only. That means this complex number is not changing the identity of the complex number Z, and Z is a general arbitrary complex number. A can be anything, B can be anything. If this result is true for A and B, that means this result is true for any complex number. That means this complex number is not changing the identity of any complex number to which it is added. So, let's consider the left hand side. This is my left hand side. This is my right hand side. See, first of all, please understand, Z is a complex number, 0 plus 0 iota is a complex number, sum of two complex numbers is a complex number. So, left hand side is a complex number, right hand side is already a complex number. I am saying these two complex numbers I have to show to be equal. When are two complex numbers equal? Only and only when their real parts are same and imaginary parts are same. So, if I have to show that these two complex numbers are equal, that means I have to show real part of the left hand side complex number, which is Z plus this complex number, is equal to real part of the right hand side complex number, and imaginary part of the left hand side complex number is equal to imaginary part of the right hand side complex number. If this I am able to show successfully, then I will be concluding that yes, these two real numbers, these two complex numbers are exactly the same, and hence Z plus 0 iota is equal to Z. Let's talk about the real part of Z plus 0 iota. So, before I talk about the real part, let us compute Z plus 0 iota. See, Z plus 0 iota. Z is A plus B iota plus 0 iota. You can add any two complex numbers. The answer is a complex number, something plus iota times something. What is this? This is real part of the sum, and this is imaginary part of the sum. Real part of the sum is sum of the individual real parts, A plus 0. Imaginary part of the sum is sum of the imaginary parts, B plus 0. And therefore, your answer is A plus iota B, which is Z. So, either we could have started with real part of the sum is sum of the individual real parts. We would have got A plus 0, which is A. In that case, I would have got real part of Z plus 0 iota equals real part of Z, because real part of Z is A. And imaginary part of sum is sum of the individual imaginary parts. So, sum of the individual imaginary parts would have come out to be B plus 0, which is B, and B is the imaginary part of Z. So, in that case also we would have got real part of this equals real part of this, and imaginary part of this equals imaginary part of this. That means these two complex numbers are same, or directly we have shown that these two complex numbers are same. That means when 0 plus 0 iota is added with Z, it does not change the identity of Z. So, I can say therefore Z plus 0 iota. Now, you know that Z1 plus Z2 is same as Z2 plus Z1 because addition of complex numbers is commutative. So, this can be written as 0 plus 0 iota plus Z. These two are same and they are equal to Z. And therefore, 0 plus 0 iota is the identity element in the set of complex numbers with respect to addition operation. And we say here 0 plus 0 iota is called the additive identity. Additive identity in the set of complex numbers. 0 plus 0 iota is called the additive identity in the set of complex numbers. That means it is the identity element. It is the identity element with respect to addition operation in complex numbers. That means when any complex number is added with it, this does not change the identity of that complex number. Any complex number. Is it clear? This is about the property 3 of addition of complex numbers. So, in the set of reals there was this identity element which is 0, and in the case of complex numbers there is another identity element which is 0 plus 0 iota. Clear? And this makes very nice sense that why 0 plus 0 iota is able to preserve the identity of the element to which it is added, because actually when 0 plus 0 iota is added with any complex number, the real part gets added to the real part. So, 0 gets added to the real part of that z complex number, and 0 added to any real number gives you back that real number. Why? Because 0 is the identity element with respect to addition in reals. So, a plus 0 is a, because adding 0 to any real number does not change the identity of that real number. So, here similarly over here. So, here we are using the concept of the existence of identity element in the set of reals with respect to addition to show and to prove the claim that 0 plus 0 iota is the identity element with respect to addition in the complex number set. Clear? So, each and every property that we have proved till now has used the concept of the same property being true in the set of reals. Fine. Talking about the fourth property. Before I talk about the fourth property, let me introduce you to a new complex number which exists corresponding to each complex number. You give me any complex number, I am going to give you this created complex number. What is this complex number? I am saying let z be equal to a plus iota b. Let this be any complex number. Then corresponding to the complex number z, there exists another complex number. So, each complex number gives rise to one new complex number. If z is one complex number, it is giving rise to this new complex number known as minus z. So, this is just the representation. What is this complex number? If minus z is a complex number, it should have some real part and some imaginary part. What is this real part of minus z? Answer is real part of minus z is actually negative of real part of z. And this blank space is to write real part of, imaginary part of minus z. And the definition is imaginary part of minus z is minus of imaginary part of z. So, what is minus z? It is, what is real part of minus z? Real part of minus z therefore has become minus of real part of z. This is real part of z and this is imaginary part of z. So, minus of real part of z, it is minus a, and what is imaginary part of minus z? It is minus of imaginary part of z, which is minus b. So, you are getting minus a plus iota times minus b. So, if z is any complex number, corresponding to z exists a new complex number known as minus z. Give me any complex number. Say for example, z is 2 plus 7 iota, then this is going to give rise to a new complex number minus z, which is minus 2 plus minus 7 iota. So, real part of minus z is minus of real part of z, imaginary part of minus z is minus of imaginary part of z. If z1 is say minus 2 plus 3 iota, then minus z1 is 2 minus 3 iota. Real part of minus z1 is minus of real part of z1. So, minus of minus 2 is 2 and imaginary part of minus z1 is minus of imaginary part of z1, that is minus 3. And if you have say minus 7 plus iota times minus 9, in that case minus z2 will be equal to 7 plus 9 iota, because in this way real part of minus z2 is minus of real part of z2, minus of minus 7 is 7, and imaginary part of minus z2 is minus of imaginary part of z2, which is minus of minus 9, which is 9. So this is how, corresponding to any complex number you pick up, there exists another complex number which is its negative. What is the role of this particular complex number? What is the role? Let me emphasize upon something over here. Now z is a complex number, minus z is a complex number. Just add these two complex numbers. What do you get? You can add any two complex numbers. When you add these two complex numbers, you get a complex number whose real part is sum of the individual real parts 2 plus minus 2, and imaginary part is sum of the individual imaginary parts 7 plus minus 7. 2 plus minus 2 is 0 and again 0. If I talk about this particular case, again if I am interested in z1 plus minus z1, what is the real part of z1 plus minus z1? That is the sum of the real parts of z1 and minus z1. Minus 2 plus 2 is 0. An imaginary part of z1 plus minus z1 is sum of the individual imaginary parts. 3 plus minus 3 is 0. If I talk about this case, z2 plus minus z2, then this is equal to what? Add their real parts, minus 7 plus 7, 0. Add their imaginary parts, minus 9 plus 9, 0. So you are watching this very carefully. It's iteratively coming out to be the same, that when z is being added with its negative, it's giving out a complex number which is equal to the additive identity, in the set of complex numbers. When z is being added with its negative, the answer is definitely a complex number, because sum of two complex numbers is a complex number. But I even know that in every case what that complex number will be, it is equal to 0 plus 0 iota, which is the identity element with respect to addition in the set of complex numbers. And this is what going to be emphasizing upon our next property. Why, how, all these things will be just clear to you. I am saying, in regard to the fourth property, I am saying there exists a complex number, or let me write corresponding to every complex number, z, there exists a complex number minus z. If I define z as a plus iota b, then minus z is minus a minus iota b. Corresponding to every complex number z, there exists a complex number minus z such that z plus minus z is 0 plus 0 iota. Thus, each complex number has an inverse with respect to addition. Each complex number z has an inverse with respect to addition, that is minus z. And minus z is known as additive inverse. What I am trying to say is, if I compare this property with the set of all reals, does this happen in reals? What happens? Does this happen in reals, that you have any real number with you? Does there exist a real number which, when I add with 2, I get the additive identity with respect to addition in the set of real numbers, that is 0? And your answer is, of course, there exists minus 2. If I say that I have the complex number minus 3, does there exist any real number which, when I add with minus 3, I get the additive element with respect to addition in the set of real numbers? Your answer is yes, of course, it is 3. and 3 is nothing but negative of minus 3. Similarly, this question was raised in the complex numbers. If you have a complex number, say z, does there exist any complex number which when you add with z, you get the additive identity with respect to addition in the set of complex numbers? And the answer was yes, of course, this exists as negative of z. That is the claim. Here we say that 2 is invertible with respect to addition, because corresponding to 2 there is existing minus 2 such that 2 plus minus 2 is equal to additive identity. And minus 2 is called the additive inverse of 2. Minus 2 is what? Additive inverse of 2. Because when it is being added with 2, it is giving you identity element. Minus this 3 over here is the additive inverse of 3. Similarly, minus z in the set of complex numbers is called the additive inverse of z, because when it is added with z, it gives you 0 plus 0 iota. Corresponding to every number, real number, there exists its own inverse with respect to addition. Similarly, corresponding to every complex number, there exists its own inverse known as negative of z. Clear? That means inverse element is existing with respect to addition, right? Inverse element is existing with respect to addition. Let us prove this claim. We have understood that when z was added with minus z in our examples, then we were getting 0 plus 0 iota. But there were just 3 complex numbers written, and they were behaving in a way that when they were added with minus of them, minus of that complex number, it was giving you 0 plus 0 iota. But is that true generally for every complex number or not? We need to generally prove this. So, if I want to show, let me just begin the proof with the very storyline. I am saying let z equal to a plus iota b be any complex number. Let this be any complex number. My question is, does there exists a complex number such that when z is added to that complex number, I get 0 plus 0 iota? Answer is yes, that complex number is minus z. That means the answer is trying to say when I add z with minus z, I get 0 plus 0 iota. Let's see. Let's see if this is true or not. I have to show z plus minus z is 0 plus 0 iota. Now z is one complex number, minus z is a complex number, so clearly z plus minus z is a complex number and 0 plus 0 iota is already a complex number. I have to show 2 complex numbers are equal, that means I have to show their real parts are same and imaginary parts are same. If I consider this complex number, consider z plus minus z. Z is a plus iota b plus minus z is minus a plus minus iota b. When you are adding 2 complex numbers, the result is a complex number. So it looks like this, something plus iota times something. And over here, what is this something? This is the real part of the sum. Real part of the sum of this and this complex number is the sum of the individual real parts of these 2 complex numbers. When you add the individual real parts, you get a plus minus a. Here comes the imaginary part of the sum. Imaginary part of the sum is the sum of the imaginary parts, b plus minus b. I just now told you, because a and b are real numbers, corresponding to every real number, there exists a real number which is minus of it, such that that real number plus minus of it gives you additive identity in real numbers, which is 0. 2 plus minus 2 is 0, 3 plus minus 3 is 0, minus 3 plus 3 is 0. So these are real, so here I get the additive identity in the set of real numbers plus iota times again additive identity in the set of real numbers. So I have got 0 plus 0 iota. Is it understood? So I began with z plus minus z, that has come out to be equal to 0 plus 0 iota. I know z1 plus z2 is same as z2 plus z1. So from here I can say this is also equals to minus z plus z, right? And therefore what have we got? We have got therefore z plus minus z is equal to 0 plus 0 iota equals minus z plus z, and this is true for every complex number z, because a plus iota b was a general complex number. This statement is true for every complex number. Therefore, every complex number is invertible with respect to addition, as every complex number z has an inverse element, that is minus z. That is it. Because corresponding to every complex number z, there exists inverse element of z, which is minus z. Inverse element itself means what? Inverse element is minus z of z, means that there exists inverse element of z, that is minus z, means when z is added to minus z, I get additive identity. That means every complex number is invertible with respect to addition. Every complex number is invertible because every complex number has its inverse element with respect to addition existing, which is negative of it. Inverse element with respect to addition existing as minus of z means when z is added with its inverse element, you get identity element. When z is added with its inverse element with respect to addition, you get identity element with respect to addition. So, all the 4 properties we did regarding addition of complex numbers were actually nothing new. We had already proved them true. They actually hold to be true in the set of reals. We just proved them to be true in the set of complex numbers by taking help of those properties being true in the set of reals, right? This is about addition. In the next lecture, we are going to talk about some more operations which can be performed among the complex numbers to create more complex numbers. That's it from my side. Thank you.